Today I'd like to give you a practical example of the use of decision matrices. And this example has actually been taken out of my consulting practice. I want to do that to sort of go into more depth on some of the choices that you have to make doing a decision matrix problem. My consulting problem was for a company that made stoneware products. Stoneware is a kind of ceramic product made from clay. And this company employs about 30 people. It's a small firm. Making things like salt and pepper shakers, sugar and creamers, teapots, flower vases and stuff like that, using what's called slip casting method. And they called me in as a consultant because they found they had a number of problems with their process. And I've listed a few problems here. First of all, in the firing process for their product, they need a human operator, and just a person to sit and watch kilns firing the clay product was extremely expensive relative to other manufacturing costs. They also found that the product was being fired poorly, resulting in a lot of scrap product. And it's quite expensive to scrap at that stage in the process because that's when it's virtually finished. They also found that they had an information problem, that they didn't really know what was going on inside the kilns when this product was being fired. They had a general quality problem, and they're in a situation of a fair amount of competition, and their customers often choose their suppliers on the basis of quality, and if they can't maintain the quality to the level of competitors, they're going to lose their market share. Also, finally, consistency. The product was quite inconsistent from one batch to the other, different colors, and that's very important if you're trying to get a matched set of tableware, for example. The color is perfectly consistent and the texture is perfectly consistent among the different products. So I looked at this problem and found it all came down to control of the kilns as an issue. And to explain this in more detail, I have to tell you a little bit about the chemistry of ceramics. Ceramics are made of clay. Clay itself has an interesting chemical structure. It's formed of crystals, very small crystals, but not crystals like grains of sand, more crystals like flat plates. These flat plates lie on one another, and they're lubricated by water, so they can slide across one another very easily. But because of the cohesive nature of water, although the plates will slide across one another, much like a wet plate might slide on a table, you try to pull it up, it won't move. It'll be held in place, just as a wet plate sometimes will stick to a table surface. And that's why clay is very plastic. You can mold it, but it's also very cohesive. It sticks together. So if you're making a clay product and you mold it into a shape or slip cast it as the company did, there's still water in it. Even if you let it dry, there's still water in it. And this water has two chemical natures, what we call water of formation and water of hydration. The water of formation is the water that's between the crystals, that it lubricates them. Water of hydration is actually water that's contained in the chemical structure of the crystal. So if you fire a clay product, that is, you heat it up, the water in it, the two kinds of water, has to escape. If you heat it up too quickly, the water escaping will turn into steam and crack the product. So you have to heat it up very, very slowly. You have to heat it up very slowly first to get rid of the water formation, the waters between the crystals. The water of hydration is even more significant in terms of cracking because it's bound up in the chemical structure of the crystals. When the crystals are heated, the water will be released. But you want that water to be released very slowly so that it doesn't crack it. So what you have to do is heat up the product very, very slowly at the beginning and then hold it for a while at a particular temperature where the water starts coming out of the crystals. So it comes out really, really slowly. If you heat it up past that critical temperature, all the water will come out of the crystals very quickly, and you'll have the steam cracking the product. So you have to hold it at a particular temperature for a long time. Once the water is out of the clay, you want to heat it up quite high to what's called vitrification temperature. And this is where the clay turns to glass. And all these little crystals that were plates all fused together into a three-dimensional structure, giving it its strength. You don't want to heat it up too hot, of course, otherwise it'll melt into a little puddle. So you have to heat it up at that very high temperature and hold it there. And you actually have to hold it there for a particular period of time because some of the impurities in the clay don't go into this glass-like structure, but instead form long, thin needles, much like reinforcing bars in concrete. That give the clay its great strength and make it not brittle like one might get in other glassy compounds. So the formation of these crystals is very important too. And to do that, you have to have just the right period of time at the right temperature at this very high temperature. Then finally, once all these chemical processes take place, you have to cool the product down slowly so there isn't uneven heat in the product, which can also cause it to crack. Now, this sequence of heat and time is what's called a firing curve. And each kind of clay in each product has its own firing curve that has to be followed very closely in order to guarantee a good product. All this chemistry is complicated even more by glazing. Glazing is a surface coating put on the product to give it color and to seal the surface against moisture loss. The glazing itself has its own chemistry that complicates the issue quite a bit. So the important thing is to control that temperature inside the kiln. There are three ways of determining the internal temperature of a kiln. You can imagine it's a difficult process because the temperatures in there get up over 1,000 degrees centigrade, which melts just about anything except clay. First way is human vision. As we know, things that are hotter tend to be more and more white. It goes through red heat and yellow heat and white heat. And human vision is actually very sensitive for our color differences. And a trained kiln operator can tell the temperature in that kiln within 10 degrees centigrade. And is probably the most accurate way of telling temperature. There are also things called pyrometric cones, which are little clay cones that are designed to melt at a particular temperature. And a human operator can look at these cones and by seeing which one is melting, tell the temperature quite closely. These pyrometric cones can also be used mechanically to release or set a switch. Thirdly, thermoelectric pyrometers are electrical devices that are made of a metal that won't melt in kiln temperatures that will generate electricity in proportion to the heat and can be used in electrical equipment to measure the heat. These are, however, quite expensive. So my consulting with the client came down to developing a set of alternative ways of controlling her kilns. There was a female company president. And I came up with a number of alternatives, really four basic ones. First of all, no automatic control. Use a human being to just sit there and look at the kilns and determine the firing curve manually. Using what's called a kiln sitter, which is a very inexpensive mechanical device that uses pyrometric cones to control in a very coarse way the firing curve for the kilns, but very inexpensively. The use of a pyrometer in the kiln and a programmable controller. A programmable controller is a special purpose computer that's used for real-time control of manufacturing processes. And thirdly, using a pyrometer and a personal computer. This project was done about 10 or 15 years ago when personal computers were fairly novel and in a way more flexible than they are today. And a personal computer could be used at that time for controlling the kilns as well as for office tasks such as accounting and word processing. Now, in fact, these last two alternatives were several different possibilities depending on what kind of programmable controller and kind of personal computer were used. But for this example, I've compressed those several possibilities into two. With the help of the client, we developed a number of criteria, which I've listed here. Installation cost, how much it would cost to put the system in place. Effectiveness, how well it would in fact do the job. Reliability, how much it could be counted on to do the job. Energy savings, energy costs for these kilns are really important. They use a lot of electricity, they're electric. Maintenance costs for supplies and breakdowns and so forth. other applications includes the office use of the computer or other uses of the human kiln operator while the kilns were in operation. And I use weightings too. I'll explain these weightings in a second, but let me show you a chart of one particular set of calculations where you see the criteria listed, the alternatives across here of a human operator, the kiln sitter, the mechanical device, a programmable controller, and a computer, and the weightings, and the final scores. Now the ratings here I developed with the client. I let her establish for me as the consultant how she felt the different alternatives met the different criteria. She also developed the criteria as well. The weights were more difficult. She found it kind of difficult to choose the weights. So most of our sensitivity analysis was concentrated on the weights. And that tends to be the case in these decision matrices problems, is that the ratings here tend to remain fairly constant. You can certainly change them, and perhaps you should under certain circumstances for sensitivity analysis. But most of the sensitivity analysis tends to be around the weights. So in this particular example, you can see where I chose some balanced weights, where the alternatives, the criteria essentially have fairly similar weights, with the cost one being just slightly higher, because costs were quite important to her. And then for the final scores, we can see that the alternative involving using a personal computer actually turns out to be the highest. But to do this properly, I had to do some sensitivity analysis. And the way I did this was to establish with her, the client, what she thought might be different ways of looking at the problem to be able to give her an understanding of how her viewpoint on the criteria would affect her decision. So what I did was to develop several different weightings based on general principles. First, the balanced one, which I showed you a second ago. And then a set of weightings that would emphasize initial cost. Initial cost was important to her. A set that would emphasize overall cost, which includes maintenance costs and energy savings. One that would emphasize effectiveness. She had to deal with her competitors and make sure that she had a good product. And so effectiveness might in fact be the most important criterion under one point of view. And in other applications. She liked the idea of having a computer to do her accounting and word processing on. And so if you put emphasis on there, that might also change the ratings. I'll show a couple of those. Here, for example, is emphasis on initial cost. You can see here I put the weight of the installation cost as 5, and the rest evenly spread with the remaining weightings available. In this case, the kiln sitter, which is the inexpensive mechanical device, turned out to be best with a total score of 60, whereas the personal computer alternative was considerably lower at 49. One more example where I emphasize effectiveness. Here again, I chose effectiveness as 5 and spread the weights evenly through the other ones. I could have chosen a different number, but that was a convenient one. And here again, the computer turned out to be the highest scoring one. These kinds of changes are quite easy, of course, if we're doing this on a spreadsheet. And the results, working with the customer, was that it really came out that the computer solution was best, except under a single circumstance where the initial cost was emphasized. So whatever other point of view we chose, that was the best solution. Now, as it turned out, the client did not buy the computer, did not go for the computer solution. She went for the kiln sitter solution. And the reason was that she was short in cash, and it was very difficult to come out with the $10,000 or $15,000 needed to implement the computer solution. We did try to get money from government sources for her, but that failed too. But you can see here that the decision matrix approach is a really good one for taking into account all of those other issues that go beyond the cost that is emphasized in most economic analyses that we've been studying in this course. Thank you.